can be observed experimentally. In particular, we already discussed previously the fact that a very important realization of the nonlinear Schrodinger equation and its solitons is provided by optical fibers, and there are very many experiments with fiber lasers, so lasers which are based on optical fibers, in which indeed, as a robust and stable mode, people observe such a breezer. So in many cases, depending on the parameters, the fiber laser can create breezers of different orders. For example, in most cases, it's a second order breezer, sometimes third order breezer, and this breezer can be observed for a long propagation distance. It can perform, actually, the fiber laser is actually a fiber loop, so it or fiber cavity. So this breezer, in many cases, performs a large number of circulations in the fiber loop, and it does not show any instability. It keeps its integrity, and this is possible because if we have the actual, if we look at the actual experiment performed with the fiber lasers, it's only approximately described by the nonlinear Schrodinger equation. But of course, there are additional factors, such as, for example, if we're talking about the laser is a real laser also have some losses, and it has some gain, because the gain must compensate the losses. And actually, the lasing itself, of course, is based on some gain mechanism. And so these additional factors, even if they consider the small perturbations added to the nonlinear Schrodinger equation, they can provide new properties, in particular because the instability of the breezer is actually a weak effect. The additional weak factors may have a chance to suppress this weak instability and provide the existence of stable breezers. And as I mentioned, often this really happens. And in many experiments with fiber lasers, indeed, the experimentalists are able to observe quite stable breezers. Even sometimes it may be possible to find a situation when the fundamental soliton is not stable, but the second order breezer is stable. So in a sense, it becomes, physically speaking, the most fundamental state in this system. Okay. Yeah, now we can discuss in some detail what I already started to talk about, namely the realization of the nonlinear Schrodinger equation in the fiber optics in some detail. So how to do this in a consistent form? So one should start from the Maxwell's equations written for the propagation of light in the optical fiber. And of course, what is important? This should be, we should of course include some nonlinearity, which means that when we write the refractive index for these optical materials in the system of the fibers of the Maxwell's equations, we take into regard that the refractive index has a correction which itself is proportional to the local intensity of the optical field. This is a famous Kerr effect, nonlinear correction to the effective refractive index. And if we take into regard this correction, we will introduce some nonlinearity into the system of the fibrous equations. Then the analysis will be rather lengthy, because the Maxwell's equations is a relatively complex system of 4 equations in a 3-dimensional space. So a number of approximations is usually applied to simplify this system and to eventually derive the effective nonlinear Schrodinger equation. In particular, this is the so-called ansatz, so the assumption about the form of the electromagnetic field, about the electric component of the electromagnetic field, which people insert into the full system of the Maxwell's equations in order to simplify it. So this assumption is that, first of all, we have the carrier wave. So everything is based on the simple plane wave. This simple plane wave propagating in the dielectric medium has some carrier frequency omega and some carrier wave number, usually it's called propagation constant, k. K is obviously 2 pi divided by the wavelengths of light. Then the electric field, as we understand, is a vectorial field. Therefore, we should fix its direction, its vectorial structure. In the simplest case, we can assume that the polarization of the field, so its direction of its vectorial orientation, is fixed just by some constant fixed vector, which is denoted by a small letter e. It's actually a unit vector which fixes the direction or polarization of the electromagnetic wave. Of course, this is the electromagnetic wave is a transverse wave. Therefore, if we consider the propagation along the axis of z, actually here, when we, as I said, we have this plane carrier wave, because we write here as a spatial coordinate z, we imply that we are going to consider the propagation of the optical wave along the z direction. So z direction will be eventually the direction along the fiber. Therefore, this vector E will be transverse to the direction of z. It will actually choose some direction in the transverse plane of x and y. Then, as concerns the dependence on the coordinates, we assume that we can factorize it, of course, approximately, not exactly. We can factorize it, so we can separately take this so-called modal function. We actually, because the optical fiber in the transverse plane provides a trapping effect. It's effectively the waveguide which keeps the electromagnetic wave trapped in its internal area. And so this trapping effect is provided just, it can be taken just from the linear from the corresponding linear solution. It's sufficient. In the solution of the linearized Maxwell's equations, also simplified somehow, will eventually demonstrate that due to the waveguiding effect or trapping effect imposed by the transverse structure of the optical fiber, the simple fact that the refractive index of glass in fiber is larger than the dielectric, than the refractive index of the surrounding medium. Therefore, light prefers to stay trapped in the material with a higher value of the refractive index inside of the optical fiber. So in terms of the corresponding mathematical, rather simple mathematical solution, it will mean that the electric field is going to be localized in the plane of xy around the central point, so localized inside of the fiber. So it's somehow, this localization function is presented by this function f, which is usually called the modal function. Modal because it describes the structure of the trapped mode of the propagating electromagnetic wave in the transverse plane. And then we assume that the amplitude remains a free variable. It remains a variable for which the amplitude of this wave, for which we are going to derive the simplified equation. So we admit that this u may be a function of two variables. Z is the propagation distance and time, but instead of time, it's more convenient to introduce a so-called local time, tau. It's time minus the propagation distance divided by the group velocity of this carrier wave. Because when, after all the simplifications that is necessary to perform, it will be quite convenient to rewrite this final equation in the reference frame, which uses instead of time this combination of time and the propagation distance, the local time, or sometimes it's called the reduced time. Okay, then also what should be said, this ansatz by itself is written for convenience in the complex form because it's quite convenient to write the carrier plane wave as a complex expression. But of course, the physical electric field must be real, and therefore the full ansatz automatically includes the second term, which is simply CC. This means complex conjugate with respect to the first term. So that the sum of the two terms is automatically real. So this ansatz, this approximation, should be substituted in the system of the Maxwell's equations. It is the system of the Maxwell's equations, which includes also, as I said, the nonlinearity of the material, the nonlinear correction to the refractive index. And after many simplifications, one will really indeed arrive at and also imposing some scaling in order to remove free parameters, one will eventually arrive at this exactly as a nonlinear Schrodinger equation. Actually, once again, two different forms of the nonlinear Schrodinger equation. The point is that as we already discussed it in the case of the equation, the same equation, but for the Bose-Einstein condensate, we could see that there were two different equations. In that case, this sign was fixed to be plus, but the sign in front of the cubic term was plus or minus. Here, if we propose a derivation for the propagation of light in the optical fiber, finally we can again derive the equation in two different forms, because now this sign in front of the nonlinearity is fixed. Why it's fixed? Because this nonlinear term represents what I mentioned already as a Kerr effect. Kerr effect, once again, it means that there is effective correction to the refractive index. It was experimentally discovered by the British physicist Kerr in the 19th century, therefore it's called the Kerr effect. So we have the effective correction to the refractive index, and this effective correction is proportional to the local intensity of the field. The local intensity is naturally proportional to the squared absolute value of the amplitudes, therefore we have this structure of the nonlinearity term, and the property of dielectric materials, such as most important among them is silica glass. The property of the dielectric materials is that this correction to the refractive index is positive. It means if we have the propagation of a sufficiently intensive electromagnetic wave, it effectively creates a refractive index for itself, which is slightly larger than it would be for the weak wave in the case of the purely linear propagation. And that, because the sign is always positive of the correction, it corresponds to the fact that in the eventual nonlinear Schrodinger equation, which can be introduced in optics, we have this fixed sign plus. Then, as I mentioned also, the evolution variable for not only for the propagation of light in the fiber, but for any problem which is called, of the type which is called guided wave propagation. So when we want to derive an effective equation for the propagation of wave guided by in some waveguide, it's quite natural to consider the evolution of this wave not in time, but the evolution along the propagation distance. And for this reason, eventually, the evolution of the formal time or the evolutional variable, it's actually with some scaling, of course, some normalized form of the propagation distance, z. And then we have this variable, tau, in comparison with the nonlinear Schrodinger equation for the Bose-Einstein condensate, for example. Here we would have the usual coordinate x. So now tau, I already mentioned what tau is. Tau is a so-called reduced time, a linear combination of the physical time and the propagation distance. And so these temporal coordinates plays the role which is usually played by the by the spatial coordinate. For example, as I said, in the case of the nonlinear Schrodinger equation for the Bose-Einstein condensate, in that case, this equation is usually called more frequently. It's called not nonlinear Schrodinger. It's called the Gross-Pitayevsky equation, but it's essentially the same. However, in the case of the Gross-Pitayevsky equation for the Bose-Einstein condensate, we always had the same sign here. We didn't have the natural derivation would give us not two different signs. It would always give us a single sign plus. And this corresponds simply to the fact that this, in the case of the Gross-Pitayevsky equation, the second derivative originates from the kinetic energy term in the linear Schrodinger equation, the commonly known second derivative with respect to the coordinates as the kinetic energy term. And the coefficient in front of this term is proportional to 1 divided by the mass of the particle. And of course, the mass is always positive. Therefore, the sign which we obtained when we derive the Gross-Pitayevsky equation, we always obtain the same sign plus. Now, in the case of the propagation of light in the optical fiber, or maybe in some other waveguide, this second derivative, it represents the effect which is called dispersion. And dispersion, this means that if we look at the group velocity of light in the optical fiber, the group velocity of light is not a universal constant. It's a universal constant if we consider the propagation of light in vacuum, of course. Then the speed of light is a constant. However, when we consider the propagation of light in the dielectric medium, even in the purely linear medium, here the nonlinearity is not important, the group velocity will not be constant. We will have different group velocities for different wavelengths of light. So this dependence of the group velocity on the wavelengths of light, this is a physical effect which is called dispersion. So dispersion, as you know, probably was experimentally discovered by Newton in the 17th century in his famous experiment when he sent the beam of white light through the glass prism, and he explicitly observed the splitting of this white light into the spectrum of different colors. And this result was possible because the white light is a mixture of many different wavelengths, each wavelength corresponds to its own color, and when each particular component with different wavelengths propagates in the material, in glass, in the material of which the prism was made, due to the dispersion effect, it would move with its own group velocity, and therefore, just because of the geometry of this propagation, it would actually be released by this prism with different spatial shifts. And this is how Newton observed the dispersion of light. Now, in most cases, the dispersion operates in such a way that when we consider two different wavelengths, then we will see that the component with the shorter wavelengths will have the smaller value of the group velocity. So the group velocity decreases with the decrease of the wavelengths. In particular, this is exactly the situation which Newton observed in his experiment, and this most typical situation is called normal dispersion. Normal just because it's the most common case. Nevertheless, in some particular situations, it may happen that for some particular interval of the wavelengths, a particular material may produce an opposite effect. And when we can compare the propagation of light at two different wavelengths, which belong to a particular interval of the wavelengths, in this relatively narrow interval, it will happen that a shorter wavelengths actually gives rise to a larger group velocity. So this opposite situation is called anomalous dispersion. Now, an important so eventually, while we obtain two different signs plus or minus in this eventual asymptotic equation, which can be derived for the propagation of light in optical fibers, this is because two different signs, they correspond to two different types of dispersion, normal dispersion or anomalous dispersion. So the bottom sign minus, it will represent the normal dispersion, and the top sign plus will represent the anomalous dispersion. Now, and the anomalous dispersion is actually, as we already actually saw in the case of the nonlinear Schrödinger equation for the Bose-Einstein condensate, we saw that the solitons could be created by this equation in the case when the signs in front of the second derivative and in front of the cubic term were the same. In that case, we can find the soliton solutions. If the signs are opposite, such soliton solutions do not exist. Now we see that here we will have solitons if we may choose here the top sign. The top sign means that it should be the anomalous dispersion. And fortunately to all this soliton physics, in the region of wavelengths which are most convenient and most important for the experiments, the dispersion of glass, of silicon glass, is indeed anomalous. Of course, it's not anomalous for all values of the wavelengths, but exactly for the interval of the wavelengths, which is essential for the experiments, it's known as an empiric fact that the dispersion of the silicon glass is anomalous. Actually, this particular value of the wavelengths, which is important for the experiment, it's a famous value 1.54 micron. It's actually it's not visible light, it's infrared light. And it's usually maybe called the mid-infrared light. Why this particular wavelength is most convenient and commonly adopted for the experiments? This happens because exactly at this wavelengths we have the minimum rate of losses of dissipation in the fiber. So the fiber is most transparent to light exactly at this wavelength. Therefore, of course, if we want to observe some non-trivial effects in optics, it's very desirable to minimize the trivial effect of losses. Therefore, the experiments are always performed usually in the vicinity of this, what is called standard telecommunication wavelengths. It's also used in optical telecommunications for exactly the same reason. Obviously, when we want to send data by means of the optical waves, we should choose carrier wavelengths which will minimize the absorption of light in the telecommunication networks. So once again, the rather lucky circumstance is that in a practically important region of wavelengths, practically important for experiments in fiber optics and generally in optics, which uses glass, the sign of the dispersion is anomalous, and eventually it gives rise to the asymptotic nonlinear Schrödinger equation derived here with a top sign. And then, as we already know, it gives rise to solitons. So this derivation analysis was actually, for the first time, the effective nonlinear Schrödinger equation for the light propagation in fibers was consistently derived in the famous work by Hasegawa and Teppert in 1973. So, as I mentioned, the classical work of Zakharov and Shabbat, which, as a matter of fact, introduced the nonlinear Schrödinger equation and introduced solitons of this equation. It was published in 1971, so 2 years later, Hasegawa and Teppert, they already were aware about remarkable properties of the nonlinear Schrödinger equation and its soliton solutions. And so what they did, they performed the analysis starting from the system of the Maxwell's equations, and eventually they ended up by deriving this effective nonlinear Schrödinger equation for the light propagation in fibers, and they actually did it. Actually, they derived both types of equations. They separately considered the anomalous dispersion and normal dispersion, but the most important prediction was made for the case of the anomalous dispersion, and the prediction was that optical solitons should be available in fibers. And so 7 years later, this prediction was confirmed experimentally in a famous experimental work by Mollenauer, Stolen, and Gordon. So this was the first work which reported the creation of solitons in optical fibers. So this is some illustration of the classical experimental result. First of all, in the left part of this picture, we see this is a situation when they would couple into the fiber a rather weak optical signal with a small power. It means that the nonlinearity was actually negligible simply because the amplitude was too small, and therefore they observed the linear propagation. The linear propagation was actually gradual expansion, gradual decay of the input signal. Then they increased their power. So if we compare this configuration when the propagation is still quasi-linear, in the first, this first non-trivial result is obtained when they took the power, which was larger by a factor of 4. In that case, obviously, the nonlinearity was stronger because the amplitude was larger. And they explicitly observed the self-trapping of this localized state with a rather sharp maximum of the intensity. And this was nothing else but exactly the soliton. Of course, it was not a completely clean soliton because it still had this additional component, the so-called pedestal. Pedestal, it was actually sort of a remnant of the initial input from which the soliton was created, because the input was not an exact soliton, so the propagation would create a soliton, but would also keep some additional component created by the input. So they were able to measure the characteristics of this object, and it was possible to identify it with full certainty as a soliton. Then they knew that if the amplitude is still made essentially higher, as we discussed it today, if we multiply the input by the integer factor, you, instead of the fundamental soliton, you will create higher order soliton in the form of the breather. And they were all able to observe this higher order breather already in the first experimental work. For example, if we multiply the input by a factor of 2, as we discussed it, so the amplitude becomes larger than by a factor of 2, then the power becomes larger by a factor of 4, and this is a situation when you can compare, for example, this configuration with a single soliton, and this configuration, so the power was larger than here, approximately by a factor of 4, a little bit more than 4. And so one should expect that in this case, probably a second order soliton, a second order breather, or second order soliton may be created. Indeed, they observed this second order soliton. In this case, actually, what we see in this picture does not seem exactly as a second order soliton. It seems as actually a configuration with 3 peaks, a tall, sharp central peak and 2 side peaks. As a matter of fact, this is, they observed it in this form because of some peculiarity of the way of the observation of the structure of the optical signal, but it could be actually deciphered in a sense and interpreted. It was possible to use this observed profile and reproduce actually the true profile of the electromagnetic wave in the fiber, which is different from this direct observation. It was necessary to transform it. And this transformation demonstrated that indeed, in this case, a higher order soliton, a breather, was also observed quite successfully. Then actually this prediction and eventually experimental discovery of soliton had given rise to a huge field of activities, because there is a rather obvious idea. It's commonly known that virtually almost all the traffic of data in the modern world is performed not with the help of copper electric wires. It's performed with the help of optical fibers. And by the time when the solitons were discovered, the optical fibers were already very widely used for telecommunications, but they operated in the linear regime. So the stream of data would be sent through the fiber in the form of linear or pulses of light, which would propagate according to the linear theory. And actually, the situation remains the same up to this day. As a matter of fact, virtually all the traffic in fiber optic telecommunication networks is performed in the linear regime. Nevertheless, a natural idea was that if one can send into the long optical fiber in the telecommunication link, instead of a weak signal, one can send a chain of solitons with a sufficiently high value of the power, so that the soliton will be able to maintain itself, propagate as a stable object, a natural idea is that each soliton may be a carrier for one bit of data. And then if we have a stream of solitons or a chain of solitons, so this is how we can send data in the binary code. Namely, we can, by definition, we can have the so-called transducer, so the generator, which creates a periodic chain of solitons. Then if then the receiver actually is adjusted to this regime of operation, and the computer which controls the operation of the receiver, it knows that at each with some periodicity in time, it must see the arrival of a soliton. So if the soliton actually arrived in this time, within the time slot which was reserved for it, in terms of the binary code, it means that this is a bit which corresponds to 1. But if within the given slot of time which was allocated for the soliton did not arrive, so simply the electromagnetic field remained essentially absent, it remained empty, the fiber remained empty in this slot, within this slot of time, it can be interpreted as a fact that there was a bit which corresponds to 0. So this is the simplest possibility to, it's called also this scenario for encoding the data into the periodic chain of solitons, where solitons is a present or is not. It's called usually this scenario or this mode is called the on-off coding. On-off means simply that when we want to send the soliton, the generator is on, and when we don't want to send the soliton, the generator is off. Well, there are more sophisticated formats which are used for transferring data, but this is the simplest one. Okay, so the idea was that if we can use a chain of solitons to transmit streams of data, maybe it will produce a new generation of optical telecommunications. Indeed, in the existing telecommunication systems, actually the nonlinearity is a detrimental effect, because it introduces some distortion into the optical pattern which should propagate in the long fiber, and this distortion induced by the nonlinearity in principle is a detrimental effect, and therefore in practical applications, engineers who design optical telecommunication networks, they try to somehow suppress the nonlinearity. Now the new idea, well, it's not new nowadays, it was new, roughly speaking, 30 years ago. At that time, a new idea was that instead of trying to suppress the nonlinearity, one can try to make it a useful factor. Namely, one can use the nonlinearity of the fiber in order to maintain a stable soliton. And then, as I said, the stream of data would be carried by a stream of solitons. So this idea at that time had drawn a huge deal of interest, and very many labs started to work in this direction, started to design such telecommunication networks based on solitons. And in principle, all this was done, and indeed the necessary components for the operation of such soliton-based telecommunication networks, they had been created, and eventually a couple of commercial companies started to fabricate such telecommunication network systems based on solitons, and they tried to sell them in the telecom market. Eventually, there was one particular company in Britain, in the United Kingdom, which which tried to sell the telecommunication soliton-based systems, and they were able to sell exactly one system. That single system was bought by some company which provided telecommunication services in Australia, and using this technology, they built a link. The length of this link was 3,000 kilometers, about 3,000 kilometers, and it connected to far-separated cities in Australia. One is called Adelaide. Adelaide is the capital of the state of South Australia, and Perth. Perth is the capital of state of West Australia. So this telecommunication link operating on solitons was inaugurated in, 20 years ago, in 2003. At that time, there was a lot of interest to it, a lot of fuss in the media, and it really started to work. But this is, as far as I know, the single commercial soliton-based telecommunication link which exists in the modern world. Because later, actually, what happened? The company which in Britain which built these telecommunication systems eventually went bankrupt because they were able to sell a single system, and the Australian provider of the telecommunication services, which installed the system, eventually it also went bankrupt. Of course, the link was already installed, it was operating, it was not thrown away. After this particular company went bankrupt, this link was bought by a much bigger company. It's a quite well-known company, Telstra. It's the main provider of telecommunication services in Australia, and it still uses this link, but it uses, as far as I know, as a backup link, because they already had the main link, which also connected the same two cities. And so, as far as I know, when the traffic in the main link was too heavy, they would reroute a part of this traffic through this soliton-based link, so it was used as a backup. Then all this big, in this big business, all the companies which offer telecommunication services, they lost interest in solitons, and the reason was that actually it became clear that using the traditional technology based on the linear propagation regime, it's still possible to provide very high bit rates for maintaining the traffic of data. So if one needs to have high bit rates, it's not necessary to switch to solitons. It's still possible to do it in the framework of the traditional technology. And of course, for this commercial providers of the services, it was very convenient, because otherwise they would not need to replace the fibers, but they would have to replace all the periphery equipment. Because of course, all these generators and receivers and all other components of the equipment which are necessary to operate the telecommunication networks in a completely different format, in the soliton-based format, it would have to be replaced. And definitely they didn't want to do it. And as they explained, even the most important problem would be not even the replacement of the equipment, but the fact that they would have to actually re-educate their staff, their technicians, because technicians were already trained how to operate the existing equipment, and they would have to be retrained for the new set of equipment. And as they explained, this would be a really very big problem. So they preferred not to switch to solitons, and nowadays this possibility to use solitons as a basis for the new generation of telecommunication networks, it remained a part of history, very interesting history, which produced many interesting results, a lot of interesting work, but it did not find a true commercial realization. Okay, so now let us return from this discussion of, so to say, industrial development to physics. And as still in the realm of optics, it's possible to consider the nonlinear light propagation in a different setting, not in the fiber, but in a different type of the waveguide. This is a planar waveguide. So a planar waveguide is schematically shown in this picture. It's a rather simple configuration. We have one relatively narrow layer, layer number 2, which is made of material with a higher value of the refractive index, and it is placed between two bulk materials, 1 and 3, with it's simply an environment, an external medium with a lower value of the refractive index. In principle, it may be air, or maybe another material with a lower value of the refractive index. So as we understand, the light always prefers to propagate in the medium with a higher value of the refractive index, so light will be naturally confined to this layer and will propagate in this direction. So this is what is called the planar waveguide. Now, it can be natural to take into regard the fact that this material in the waveguide may also have its nonlinearity, the same kernel linearity that we already discussed for optical fibers. And it may be interesting to try to derive the effective propagation equation for this planar waveguide, taking into regard the nonlinearity, and as a matter of fact, we will again end up with the effective nonlinear Schrodinger equation. Physically, of course, it will be derived in a very different situation, but mathematically, it will keep the same shape, and then it will make it possible to predict solitons. So the particular derivation is based on the ansatz. So again, it starts from the Maxwell's equations, and the material properties when should be inserted in the Maxwell's equations are again taken to regard the Kerr effect, that is the fact that the refractive index has a nonlinear correction. So then the appropriate ansatz for the electric component of the electromagnetic field is written here. Again, it's a vectorial field. Again, this small bold letter E implies that this is a fixed vector which determines the fixed polarization of light. Of course, it's a transverse wave, so we again consider the situation when the propagation direction will be called Z, coordinate Z, and then each is polarized, is oriented perpendicular to Z. For example, it may be oriented along the axis of Y. Then we have, similar to what we discussed in the case of the optical fibers, we have here the carrier wave in the form of as a plane wave simply, with the frequency omega and some propagation constant of wave number k. It's once again 2 pi divided by the wavelengths of the carrier wave. Then we, as we already discussed it qualitatively, we assume that due to the difference in the refractive index, the light remains essentially confined in this intermediate layer and does not penetrate deeply into surrounding layers 1 and 2. This means that the structure of the field in this direction along, so if we call this coordinate y, the structure of the field along y will be essentially localized, and it can be approximately described by the so-called modal function, which can be just obtained from the solution of this relatively simple solution of this problem is a purely linear approximation. So this modal function is f of y, schematically written here, and then there remains an amplitude, capital U, which is allowed to be a function of x and z. So what is essential here? Previously, maybe we can jump back to the similar answers which we employed for the fibers. In the case of the fibers, let us look at this ansatz. We assume that this free amplitude could be a function of z, of the propagation distance, and eventually we derive the equation where z was a formal time. It plays the role of the evolutional variable. Physically, it's not time, it's a propagation distance, but it was a formal time, the evolution variable. And then tau was effective coordinate, was actually, physically speaking, was a temporal variable. So here there was u was not a function of x and y. All the dependence of x and y was concentrated in this modal function in the transverse plane, and we assume that effectively the amplitude was allowed to be a function of two variables, z and tau. And by the way, of course, when we use this factorization, another essential assumption which is used is that we have the z dependence here and we have the z dependence here. And the derivation proceeds by assuming that actually this simple expression is a rapidly varying function of z. It just rapidly oscillates, obviously, as a function of z due to the linear phase. And this capital U is allowed to be an arbitrary function of z, but it's a slowly varying function in comparison to the rapidly varying carrier waveform. And for this reason, when we derive this effective equation, we obtain the term only with the first order derivative with respect to z. Indeed, we understand that as we know, the Maxwell's equations, they can be reduced to the wave propagation equation. As a wave propagation equation, it's roughly speaking something similar to the Lambert equation, roughly speaking. So the wave propagation equation by itself is the second order equation, which would have the second derivative with respect to z and the second derivative with respect to time. Now, how we, in this derivation, how it happens that we eventually obtain, instead of the second derivative with respect to z, from which we start, we will eventually only have the first derivative. The point is that when we substitute this ansatz into the second derivative with respect to z, we have the following option. First of all, we can differentiate twice only this rapid dependence, but this will give a term which will be automatically be cancelled with other terms in the zero-order approximation. Then, when we this effective equations that we want to derive is obtained in the first order approximation. In the first order approximation, we can differentiate once the rapidly varying function and once the slowly varying function. So it will give a smallness of the first order, because the derivative of the slowly varying function is something small. But we neglect the additional contribution when we twice differentiate the slowly varying function, because it will give smallness of the second order, it is neglected. And therefore, when we have this mixed term, I mean we once differentiate this exponential and once differentiate u, therefore we obtain eventually, in the eventual equation, this common exponential factor is cancelled, but what we keep as a result of the differentiation is I. When we perform the first differentiation with respect to I, with z we obtain obviously the factor of I. So this factor of I is kept here, and then we have the first derivative of u with respect to z. That's how we arrive at this term. Now, instead of this ansatz, we adopt the ansatz for this planar waveguide, which is written here. So what the difference is? The difference is that we assume that the time dependence is represented solely in this carrier wave. We don't admit any possibility. We simply don't want to consider the situation when this slowly varying amplitude will be a function of time. So we are going to derive effectively the equation which will have no time, but still it may be non-trivial equation, because we may have, instead of time, we know that the evolutional variable in any case will be z. And so eventually we would like to derive an effective equation with two independent variables. One will be z along the propagation distance, and the second will be transverse coordinate x. So in terms of this picture, we will have z propagation along the propagation direction, x in this direction in which we have is a long direction of this layer of this waveguide, and y, the third coordinate is a transverse direction, which will be naturally eliminated by the derivation. So, and of course, we should, all this term is complex, and once again, we should add it mathematically as a complex conjugate part in order to have the real electric field. So then the analysis proceeds by substituting the ansatz into the full system of the Maxwell's equations, performing all kinds of simplifications. In particular, we play the same game to reduce the second order equation to the first order equation, because once again, when we have the ansatz in the wave equation to which the Maxwell's equations are equivalent, we will have originally the second derivative with respect to z, And then we say that we assume that this carrier exponential wave is a rapidly varying function of z, which means k, in a sense, is a large parameter, while this arbitrary amplitude u may be a function of z, but a slowly varying function. And so when we formally must calculate the second derivative with respect to z, the non-trivial contribution will be given by the term when we once differentiate the rapidly varying function and once differentiate the slowly varying function. The differentiation of the rapidly varying function will give us a factor of pi that will appear here. And then the derivative of u with respect to z will give us the first derivative. And this way we will arrive eventually at the first term in the effective nonlinear Schrödinger equation. Then the second term, it's a very simple, its physical origin is very simple and obvious. When we have the propagation of electromagnetic waves, of course, we always have the effect of diffraction. So the expansion of light in the transverse direction. So if we launch some beam of light into this waveguide, which simply, when it is coupled, when it is launched, is made localized with respect to x, to this coordinate, it will start to spread out, to stretch itself in the x direction. And so this is the effect of diffraction. And the effect of diffraction after rescalings will be naturally represented by this second order term. Now this is the second order derivative with respect to the coordinate x, transverse coordinate, or the coordinate along the coordinate which is running in the long direction of this planar waveguide. And then we have finally the cubic term, and the cubic term has the same origin as in the case of the fiber propagation, namely it takes into regard the Kerr effect, the nonlinear correction to the refractive index. So this is the final equation which can be derived asymptotically for the light propagation in the planar waveguide. And what we see that first of all, it should be stressed that when we derived it for not it, but a similar equation for the optical fibers, in that case we had actually two different equations, because physically we might have, as we discussed it, two different signs of the group velocity dispersion. This is the coefficient in front of this term, when this was the second derivative, not with respect to x, but with respect to the temporal variable. Now, here, instead of the group velocity dispersion, we have the coefficient of, instead of this dispersion, we have diffraction. And the diffraction coefficient is removed. It's, by rescaling, it's equal to 1. But an obvious fact is that diffraction always has the same sign. We cannot have normal or anomalous diffraction. Diffraction is a very simple, purely linear effect. And when we have the propagation of light in any waveguide, diffraction always has the same sign, because the diffraction actually drives the expansion of light, but it cannot suddenly start driving the self-compression of light. And this is the reason why we have only one option for the sign. And then a fortunate circumstance is that we obtain this equation when both signs in front of the second derivative and the cubic term are identical, plus and plus. So if we compare it once again to what we could derive in the case of the light propagation in fibers, this combination of signs, maybe I already passed it, I think. Yes, let me go to the correct page. Here, yes. So for fibers, we could derive this plus or minus. Now, and we said that solitons are possible for the anomalous sign of the group velocity dispersion, so for the top sign plus. Now, formally speaking, the effective equations that can be derived for when we have the diffraction instead of the dispersion, it also produces sign plus. So formally speaking, we can say that the spatial diffraction is similar exactly to the anomalous group velocity dispersion, but it's opposite in its sign to the normal dispersion. So in other words, normal diffraction is something which is similar not to normal dispersion, but to the anomalous dispersion. But eventually, if we have this effective equation, we understand immediately that it may also produce its soliton solutions. Now, because we don't have a temporal variable, it will not be a soliton with any structure in time. So it's what is called the spatial soliton, or because it does not include the temporal variable. Or solitons in what is called also the spatial domain. Solitons are optical fibers, they are called solitons as a temporal domain because they are localized essentially with respect to the temporal variable. The temporal variable explicitly appears there. Here the temporal variable does not appear at all. The localizations that we may have obviously will be with respect to x. So this will be spatial self-localization. So it will be, in terms of this waveguide, the soliton will be a beam of light which propagates, supports its stable propagation in this setup, and it will be localized with respect to this coordinate axis. So it will be localized, roughly speaking, around the symbol 2. It will be localized, it will support its self-trapped localized state, and will be, so it means that actually nonlinear self-focusing, which is induced by the Fourier effect, will be able to exactly balance the self-stretching, which is driven by the diffraction, and therefore we will be able to create a stable solid. So after this prediction was made, the equation was derived for the planar waveguide. It was predicted the solitons may exist, so some experiments were performed later than they were performed for the temporal solitons and fibers, and for the first time, explicitly such spatial solitons were observed in 1988 in this particular work. They used some liquid dielectric material, so they had a planar waveguide which was filled with some liquid material, and this liquid material had then sufficiently strong nonlinearity. But because the most important material in optics is silica glass, people also tried to create such planar, spatial solitons in the planar waveguide made of glass, because it will be easy to integrate it with all other optical elements in any setup. And for the first time, spatial solitons in the glass waveguide was created 5 years later in this work. Okay, now, in both cases, in optics, which we discussed today, solitons are effectively one-dimensional objects. Of course, the setup that we considered is not one-dimensional. For instance, here in this geometry, essentially, we can say that it's three-dimensional because we have the transverse coordinate y, we have the propagation coordinate z, and we have this coordinate x along the waveguide. However, this transverse coordinate y was eliminated by the derivation. And then z, of course, remains, but z, formally speaking, does not play the role of the coordinate. It plays the role of formal time of the evolution variable. So as an explicit coordinate, in the final equation, we have only x. Therefore, we can say that this is an effectively one-dimensional equation, and solitons, which are predicted by it and which were created experimentally, they may be naturally considered as effectively one-dimensional solitons. Similarly, temporal solitons and fibers are also considered as essentially one-dimensional solitons. Now, it's nevertheless possible to consider more general propagation of light in the bulk material, so to say, it's a three-dimensional optical waveguide. And in that case, one can also adopt some ansatz for the electric field, insert it into the Maxwell's equation, and try to create a more general propagation equation, actually, not with a single free coordinate, but with two free coordinates. So the possibility is suggested by this ansatz. So once again, we are going to consider the propagation of the electromagnetic wave along the axis of z. Therefore, this is a carrier wave. And once again, the carrier wave with frequency omega and propagation constant, the wave number k. Then again, because it's a vectorial field, as we did before, we assume that this vector small e fixes a particular polarization of light as just a constant polarization, constant direction of light, of the electromagnetic field in light in the transverse direction. So it's this vector belongs to the plane of x and y. Then we assume that the free amplitude, which we write here, capital U, it is allowed to be a function of three coordinates, x, y, and z. And so x as a function of x, all the dependence on x and y that we may have according to the Maxwell equations is actually represented by this amplitude U. We don't have the explicit x and y dependence elsewhere. As concerns z, we adopt the same assumption which we adopted previously, namely, we assume that the dependence on z may be arbitrary, but it must be slow in comparison with the rapid dependence on z in this carrier expression for the carrier wave. So then, again, what we will have to do, we will have to, first of all, as it's well known, the Maxwell's equations can be reduced to the wave equation, second order equation. It will be the fully three-dimensional equation. And then when we will have to calculate the second derivative with respect to z, we will adopt the same approximations. Non-trivial contribution will be made by the cross term when we once differentiate this rapidly varying factor and once differentiate the slowly varying factor. This will, once again, the differentiation of the rapidly varying function will give us this familiar factor of I. This common exponential factor will be eventually cancelled. And then we will keep the first derivative of u with respect to z. This is what we have here. And now, in comparison with the previous equations that we discussed, because previously we allowed, in this ansatz, we allowed the dependence of u, arbitrary dependence of u only on one transverse coordinate, on x. And y was essentially eliminated by this modal structure, by the fact that the light was strongly confined in the y direction. Now we consider the uniform medium without any confinement, and therefore, in this generalization of the ansatz, we can assume that we don't have any such modal function, and therefore u is allowed to be an arbitrary function of both x and y. So this is what we adopt in this ansatz. Again, we take the complex ansatz, we add the complex conjugate term to make the electric field real. We substitute this ansatz in the system of Maxwell's equations. Actually, as a matter of fact, we first reduce the system of the Maxwell's equation to the wave equation, second order equation, and substitute this ansatz. As I said, for the evolution term, we will obtain this with a factor of phi, the first order derivative of u with respect to z, and then we will have a combination of second derivative with respect to x and y. This is a direct contribution from the second order derivatives with respect to x and y, which we have in the three-dimensional wave equation. So the term is simply transferred from the wave equation, essentially. And then, as before, we have again the cubic term, and once again, it has the same meaning as before. So it represents the effective nonlinear correction to the refractive index. It's a clear effect. So what we derived here may be naturally called the two-dimensional version of the nonlinear Schrodinger equation, because now it has not a single coordinate x, but it has two coordinates, x and y. And the question is, what solutions can this equation predict, and if it's possible to observe them experimentally? So first of all, it's necessary to stress that the integrable nonlinear Schrodinger equation, this is a one-dimensional equation. The two-dimensional equation, which is written here, is not integrable. We cannot find any exact solution. By itself, it's not a very big problem because it's easy to use numerical methods in order to construct solitons by means of a computer solution. In particular, a rather natural idea is that we can try it because we have soliton, which must have some structure in the plane of x and y. The simplest possibility is to assume, so in this plane of x and y, we can introduce, instead of the Cartesian coordinates x and y, we can introduce the polar coordinates. This will be r and theta. Actually, here theta, the angular variable, is not explicitly written, does not appear. And then the simplest answer for a solution is written here. So we can have some real function, capital V, which is assumed to be just a function of the radial variable, because we assume that we are going to have a solution, a soliton, with the axial symmetry, isotropic in this plane. Therefore, we have no dependence on the angular variable, and we assume that the structure depends only on the radial coordinate. And so, of course, it should be localized because we want to construct a soliton. It means it should vanish when r takes very large, when r goes to infinity. This function b must decay to 0. It must be localized. And then we may have, of course, this factor with propagation constant q. Actually, when we derived this equation from the ansatz, we originally had this propagation constant k, but this constant k was eliminated in the course of the propagation. It does not appear explicitly in this equation. Now, in the framework of this equation, we can say that the particular solution may have this q, and q will be, as a matter of fact, an additional propagation constant, additional wave number added to the original one. But according to the meaning of the derivation, k is a large wave number, a large propagation constant, and q, physically speaking, is a very small correction if we want to construct the total wave number. Okay, so then one can substitute this ansatz in the equation, derive a simple radial equation for v. It's enough to assume this function v may be real, and then, because this equation, unlike the one-dimensional Schrödinger equation, we can solve this equation analytically, but it's very easy to solve it numerically. And we can construct, as a matter of fact, a family of such solitons, because they exist for all real values of q. And not for all real, it's better to say for all positive real values of q. So we will have a family of solitons. So these solitons are usually called Towns solitons. Okay, why they are called Towns solitons? Because historically speaking, the solitons which can be produced by the two-dimensional nonlinear Schrödinger equation, if we substitute the simple ansatz, historically speaking, this is the first soliton which was ever theoretically considered in optics. And this solution was proposed in 1964, long ago, almost 60 years ago, in a theoretical paper by 3 people. And the third author was Towns. Towns was a very famous optical physicist, and because even if he was the third author, these solitons are called commonly Towns solitons. So, as I said, historically, it is the first case when solitons were introduced theoretically in optics. And by the way, for the very first time, they were introduced not in the one-dimensional form, but in the two-dimensional form, even more complex than one-dimensional. And also what may be mentioned is the fact that in 1964, the word soliton did not exist. This, we will still talk about it a little bit later, but the word soliton, this term, was coined in a famous paper in terms of a completely different equation. And we will discuss it a little bit later. Korteweg-de Vries equation, KdV equation. And this soliton, as a name for the localized wave solution of the KdV equation, was coined as a term in a famous paper by Zabusky and Kruskal in 1965. And this numerically found solutions for the Towns solitons, they were published in 1964. So at that time the word soliton did not exist. Therefore, they called this what we would now we would call solitons. At that time, they called it self-trapped beam of light. Self-trapped beam of light because it was a beam in the spatial domain, localized in the plane of x and y without any temporal coordinate, without any time dependence. And so the point is that in optics, later, many different types of solitons have been experimentally observed, as again mentioned today. For example, these were famous solitons in optical fibers, and also solitons and planar waveguides. But this Towns soliton, which was the first time predicted, has never been observed in optics. And the reason is that unlike one-dimensional solitons that we already discussed, this two-dimensional soliton is completely unstable. This is why it's not possible to create it experimentally. Actually, the fact that it's unstable was, of course, found theoretically. It's not very difficult to understand that it is unstable. And it is unstable against a specific effect, which is called the collapse. Collapse is actually a possibility to have a particular solution of this equation, which will, in the form of the catastrophic self-compression. So in this two-dimensional equation may give rise to solutions which demonstrate, which they start from some localized input, then due to the nonlinear self-focusing nonlinearity, this input starts to compress itself, and eventually, unlike in the one dimension, it will compress itself into a soliton. In two dimensions, it does not stop by forming a soliton, but it actually continues the self-compression in the catastrophic form, and eventually, after finite propagation distance, or finite evolution time, in other words, it ends up with the formation of the true mathematical singularity. So this means the solution ceases to exist as a mathematically relevant object. Of course, in the physical situations, that true singularity cannot appear, but it means that it's possible to observe some blow up, very strong self-compression of light, and indeed in the experiments, it could be observed. And now this is the illustration of the collapse. So what is shown here is an example of the numerically simulated solution of this two-dimensional nonlinear Schrödinger equation. What is shown is the evolution of the cross-section, because we can see the solitons as actually only as a function of R. We can plot the evolution of this dependence, or the matter of effect of this function V on R. So we start from this localized input. Actually, this localized input exactly corresponds to the numerically found Towns soliton. And then we allow it to evolve according to the equation. And originally, it seems that it remains stable. However, gradually, the perturbation will start to grow. Not immediately, but relatively slowly, the perturbation will start to grow. Then its growth will self-accelerate, and after some finite, here is called the evolution variable time. After some finite evolution time, we will observe the formation of a true singularity here. This final profile implies that we are very close to the infinite value of the field, to the singularity. By the way, this is the original stage of the evolution. Original stage of the onset of the instability is slow. As you can see here, really, we don't have a very quick growth of the instability. Originally, it seems as if it is almost stable. And the point is that this particular perturbation mode, which initiates the growth of the instability, this mode does not grow in time exponentially. So it does not grow fast. It grows in time as a matter of just slowly, something like square root of time only. Actually, we already talked today about another slow instability. The instability is a one-dimensional nonlinear Schrödinger equation. The instability of the breather as a bound state of fundamental solitons along the possible splitting into constituent solitons. And as I said, in that case also this instability may exist, but it will be slowly growing instability because the effective perturbation would grow linearly in time. So something similar happens here. It's a slowly growing instability, but eventually it self-accelerates, and eventually it will destroy the soliton by transition to the collapse. Now, for this reason, such Towns solitons have never been observed in optics. Nevertheless, recently they have been observed experimentally in a different physical setting. We were talking already many times about the fact that the nonlinear Schrödinger equation can be derived, as a matter of fact, exactly in the same form as in optics, also in the application to the Bose-Einstein condensations, with the difference that in that case, the equation itself usually is called the Gross-Pitayevsky equation, and the evolutional variable will be time, not z. But here, x, if we want to consider the two-dimensional case, x and y gives the same meaning. They remain two transverse, simply two spatial coordinates. So it's possible to derive an equation, as a matter of fact, in exactly the same form for the effectively two-dimensional Bose-Einstein condensate. And then actually experiments for some condensates can be performed in a well-controllable and very clean setting. And because the original evolution of the instability is slow, one can actually try to experimentally observe this evolution of the town soliton at the stage when still the growth of the instability is very slow, so soliton practically may seem as a stable object. So this was indeed demonstrated in a relatively recent experiment with the Bose-Einstein condensate. So this is some pictures taken from this experimental report. First, this is a snapshot which demonstrates the distribution of density in this two-dimensional condensate. So you see that the characteristic size. So here we see that all the density is concentrated to the center. So this is distribution of the density, which is observed after some evolution time. So it's still a quasi-stable soliton. If the experimentalist would wait longer, eventually this soliton will be destroyed by the collapse, but later. So here it was the evolution of the growth of the perturbation was sufficiently slow to make it possible to observe the effective stability of the soliton over the time of the observable interval of time, not extremely short interval of time. And as you see, this here, the characteristic size of this soliton in the transverse direction is in the BEC, it's roughly speaking 10 microns. So it's not extremely small, and therefore it's rather easy to observe details of its structure in the experiment. And this is actually the transverse structure, explicitly transverse structure of the soliton, which was also extracted from the experimental data. So this is a transverse structure. So this is the transverse structure of the density of the soliton. And so we see that indeed this is a well-localized isotropic, because it's, well, here in this picture, it's not completely isotropic. There are some inhomogeneities, of course, but in the one can, roughly speaking, average the result with respect to this anisotropy in the azimuthal direction. And then one will have, obviously, if we take the structure of the density along the radial coordinate, we will have the transition from the maximum at the center to the gradual decay far from the center. This is exactly what we see in this picture. Then the next step is that if we can this way produce town solitons as the simplest type of solutions to the two-dimensional nonlinear equation, it can be also taken in a more general form. Namely, now we can recollect that we also have the second radial variable, the second coordinate, the angular coordinate theta. And then it's quite obvious that we may try to construct an answer for the solution when we insert into the two-dimensional nonlinear equation not simply some function of the radial variable, but also the space factor, e to the power I s theta. Of course, s must be integer number, which is usually called the vorticity. It may be also called the topological charge, because this phase structure actually makes this solution what is called the topological soliton, with embedded topological charge. And again, it's possible to substitute the answers into the two-dimensional nonlinear Schrödinger equation and numerically solve it. and obtain a family for each fixed value of S. We can obtain a family of such solitons. So if S is equal to 0, we will return to what is called fundamental bound solitons that we discussed right now. If we take S equal plus minus 1, plus minus 2, and so on, we will obtain families of vortex solitons. The problem with vortex solitons in this case is that they are subject to much stronger instability. So the fundamental soliton, as we discussed it, is unstable in principle because it develops as a collapse, but it develops it originally slowly. And this fact made it possible recently to observe such solitons as quasi-stable objects in the sea. As concerns the vortex solitons, they are also in principle unstable against the collapse, but this is not the main danger for them. The danger is the fact that they are unstable against another perturbation, which actually breaks their axial symmetry. So this is an azimuthal perturbation, and this azimuthal perturbation is a function of the angular coordinate theta. And so what happens is this picture. First of all, if we look at this radial structure, f of r, of this vortex soliton, we see that unlike, for the fundamental soliton, we had this simple structure. Now, for the vortex soliton, the value of the field cannot be finite at the center. For example, if you take vorticity S, obviously at small values of r, asymptotically this field must decay as r to the power s. It's simply the same obvious asymptotic form as we know from the Bessel function. For this reason, so what we expect from the vortex soliton is localized at infinity, but also localized as r goes to 0. Therefore, if we look from above, we will see some ring structure, ring-shaped structure with the maximum of the density in the middle. So we will see something like this. So this is the top view for the distribution of density in the vortex soliton with vorticity 1, and this is a similar picture, but when the vorticity is 2. Now, when we had the fundamental soliton without vorticity, it was only unstable against collapse, but there was no instability which would try to spontaneously break its axial symmetry. When we have this vortex soliton in the form of the vortex ring, it's most vulnerable not to the collapse. It's vulnerable to another perturbation which breaks the axial symmetry, and what it's trying to do is tries to split this ring into a set of fragments. So in the simplest case, when vorticity is 1, it is unstable against spontaneous splitting in a pair of 2 fragments. You can see. So this is shown, this is the evolution show. This is the input. Input is the form of the numerically exact stationary vortex soliton, which was found as a stationary solution. And then this is a result of the evolution of this input in the framework of the 2-dimensional nonlinear Schrodinger equation. So it's here it initiates the splitting, and here it's already well split into 2 fragments. So each fragment, roughly speaking, can be identified as a fundamental soliton. Actually, it's not quiescent. It's not a standing soliton. It is moving in some direction. Why it's moving? Because obviously the input has some angular momentum. Vorticity is, of course, related to the angular momentum, and the evolution governed by the nonlinear Schrodinger equation, of course, must conserve constant value of the angular momentum. So in this final form, the angular momentum is simply the angular momentum which is related to the fact that these fragments are moving. And much later, each of them will be also destroyed due to intrinsic collapse. Now, a similar outcome happens if we try to simulate the evolution of the soliton with a higher value of the vorticity, namely 2 instead of 1. So in this case, it's a ring which is much broader with a very broad also internal hole. And it starts, in this case, it's most vulnerable to the spontaneous perturbation, small perturbation, which tries to split it into a set of 4 fragments. And then eventually, we see that it was split into this set of 4 fragments. Again, each of them can be approximately identified as a fundamental soliton. Each one is moving because, again, this configuration must conserve the angular momentum of the input. This set of fragments conserves the angular momentum because it is moving. And much later, each fundamental soliton, each fragment will blow up and will be destroyed by the intrinsic collapse. Then the analysis can be continued. I mean, the derivation of the multidimensional Schrödinger equations, particularly if we do it in optics, and eventually, if we understand in principle how this equation could be derived in 2 dimensions, it can be derived in the most general form in 3 dimensions. So in that case, the answers will be similar, but now we assume that function u may be a function of x, y, z, and also of time. And then the assumption, similar to what we adopted for the derivation of the nonlinear Schrödinger equation for fibers, is the fact that the time dependence appears both in this carrier wave and in the amplitude. But we assume that in the amplitude, it is very short. This is a slow dependence with respect to the rapidly varying carrier wave. So then, in the fully 3-dimensional geometry, we use the 3-dimensional wave equation, to which, as is well known, the Maxwell's equations may be reduced. Of course, we keep the nonlinearity once again, introduced as a correction to the refractive index. And then again, when we need to apply the second derivative with respect to z, we again say that the first non-trivial contribution will be produced by the mixed derivative when we differentiate once the exponential and obtain the factor of I, and once differentiate the amplitude, and so we obtain the same term as we already saw here. Then these 2 terms will be obtained. They actually represent diffraction. It's the same way as they obtained in the 2-dimensional case, because we, in the full wave equation, of course, we have second derivative with respect to x and y, and we essentially carry them from there. And then we will also have, because now we adopt the possibility of the dependence on time, and we have the second time derivatives in the wave equation, we will also obtain, in addition to this second derivative, the new second derivative, namely the second derivative with respect to time. And this way we will arrive at this 3-dimensional nonlinear Schrödinger equation, which is valid in optics. But it should be said here that about the sign in front of this new term, the second, so tau is the same, exactly the same reduced to local time that we discussed in the case of the fiber. So this is, maybe I can jump back to its definition. Yes, here. So this we introduced this temporal variable in the case of the fiber, exactly this, because we still have the carrier wave, and we have the group velocity of the carrier wave. We can define exactly the same reduced temporal variable when we are trying to derive the 3-dimensional nonlinear Schrödinger equation, and it means we end up with this 3-dimensional equation where the role of the third coordinate in the second derivative is written with respect to the formal third coordinate is actually the temporal coordinate, the temporal variable, formally speaking, the temporal coordinate. Now, here the sign is written as plus, but as we discussed it in the case of the fiber, actually the sign depends on the sign, or the physical sign of the group velocity dispersion in this material. So it may be normal or anomalous. So after all the rescalings, the coefficient will be +1 if from the start we assume that we have the anomalous group velocity dispersion. And this is the most interesting case because once again, this case can help us to create solitons. If for physical reasons the underlying dispersion is a normal dispersion, we will derive a similar equation, but the sign here instead of plus will be minus. If it's minus, we cannot have three-dimensional solitons. If the sign is plus, we can have the three-dimensional solitons, but they will be strongly unstable. So again, we can first of all construct a fundamental soliton. Fundamental will be in terms of this three-dimensional space with coordinates x, y, and tau. We can say that this is three-dimensional space is actually a spatial-temporal continuum, strictly speaking, because one of the coordinates is temporal. In any case, it's possible to construct isotropic solitons in this three-dimensional space. They represent fundamental solitons. They exist as families, but they are unstable and against the collapse. And actually, this instability is stronger because now they will be unstable against the perturbation, which originally grows exponentially. As I mentioned several minutes ago, when we consider the two-dimensional nonlinear Schrödinger equation, we have the instability driven by the collapse, but originally this is a very slowly growing instability because it does not grow exponentially. Now, in the three-dimensional case, this instability driven by the collapse will immediately grow exponentially, so it will very quickly destroy a three-dimensional soliton. Then one can also construct three-dimensional soliton which will carry the embedded vorticity. So now of course, this soliton is not spherically symmetric, but it is axially or cylindrically symmetric, because if we introduce the vorticity, still it remains isotropic in the plane of x and y. So if we try to look at the three-dimensional distribution of the local intensity, it will seem like a torus, or sometimes this object is called a donut. So this is a torus with embedded vorticity, but it's similar to what we discussed a few minutes ago. For the two-dimensional vortex solitons, these three-dimensional vortex solitons are strongly unstable, first of all, even not against the collapse, but against spontaneous splitting. So what happens in this direct simulation, we will see that this was a three-dimensional vortex soliton with vorticity 1, and it spontaneously splits rather quickly in a set of two fragments. Each fragment can be approximately identified as a three-dimensional fundamental soliton, and in the course of the subsequent evolution, it will be destroyed, somewhat slower, but it will be destroyed by the intrinsic collapse. Then this broader vortex, broader torus, with larger size of the torus, it represents a three-dimensional soliton with embedded vorticity 2. And it is also strongly unstable this time, similar to what we saw a few minutes ago. It was a case of vorticity 2. The vortex soliton in this case splits spontaneously into a set of 4 fragments. So the angular momentum is conserved because these fragments are moving, and each of them can be approximately identified. Each fragment can be approximately identified as a fundamental soliton, and later it will blow up, it will be destroyed by the intrinsic collapse. Okay, so we have, for the time being, we have completed a part of all this long lecture, which aimed to introduce the nonlinear Schrödinger equation, including its modifications, such as what is called the Gross-Petaevsky equation, and its different version of this equation in spaces of different dimension, 1, 2, and 3. Now, there are some other very important nonlinear equations, which are interesting as both mathematical objects and due to their physical realizations. And as the next important equation, in a sense, it can be called ubiquitous. Ubiquitous, it means it occurs in the same form in many very different physical situations. So this equation is a one-dimensional equation. It's equation for the real unknown function phi, not complex. It's a second-order equation because it has second derivatives. Now t will be the evolutional variable, x is the coordinate. This is a nonlinear term, sine of phi. And this equation is called the Sine-Gordon equation. The origin of this name, Sine-Gordon, is that first, it's possible, of course, if we want, we can consider, first of all, the approximate form when the local amplitude will be small. So phi may be positive or negative because it's real variable. Its local value may be positive or negative, but its absolute value will be small. We can consider solutions when absolute values of phi are small. I'm speaking about absolute values because it may be positive or negative. Then, for such a solution with a small amplitude, we can first of all linearize the equation. Instead of sine of phi, we can approximately write simply phi. The first term is the Taylor's expansion of sine. And this way, we will obtain the linear equation. And this is the linear wave propagation equation, which is well known as a classical wave propagation equation. And such an equation with sine of phi replaced simply by pi, it's called the Klein-Gordon equation. It was introduced by also Klein-Gordon, roughly speaking, a little bit more than maybe 100 years ago. Now, when this Sine-Gordon equation became important, how people developed this name, they took this commonly known name of the Klein-Gordon equation, they dropped Klein, and replaced it by word sine, by the name of this function, sinusoidal function sine. Therefore, this Sine-Gordon equation was given its name. But in mathematics, this equation, as we will discuss in a couple of minutes, this mathematics has been known, even if it was not called this way, it was known for a very long time, actually, start from the 19th century. Now, as concerns, before discussing some mathematical properties, it's necessary to say that this equation finds some very important physical realizations, and arguably the most important physical realization is in the form of what is called the Long-Josephson junction. So the Long-Josephson junction, this is a system which includes two superconductors, two what's called bulk superconductors. So this is the simplest possibility. This is one bulk superconductor. This is another bulk superconductor. And they are separated by a very thin layer of a dielectric material. Now, what may happen in this in this physical system? We know that the super current in the superconductor, in each bulk superconductor, is carried by what is called Cooper pairs. Cooper pairs are bound states of electrons with opposite directions of their spin. Now, this this material will remain superconducting as long as the Cooper pairs are stable. They do not split into individual electrons. And if this dielectric layer is thin enough, the Cooper pairs may also tunnel, jump across this barrier from one bulk superconductor into the other, keeping the integrity, keeping the bound state. So this means that we may have effectively tunneling of the superconducting current between two superconductors across the narrow dielectric lane. So this is a cross section, actually, of the system, which shows typical scales which people use in the experiments, so that typically the thickness of the bulk superconductors is several hundreds of nanometers, while the dielectric layer has a width of only a few nanometers. Okay, so Then, so it was Josephson who theoretically introduced this configuration, and he performed the analysis, and he derived some effective equation which governs the dynamics of this superconducting system. And this equation actually turns out to be exactly the Sine-Gordon equation. So in the case of the Josephson junction, yeah, by the way, the Josephson junction may be not, this is a linear Josephson junction, non-linear Josephson junction, but it may also is available in the experiment in the form of a ring-shaped Josephson junction. Okay, so in the derivation of Josephson, the variable phi, it has the meaning of the phase difference, namely, in terms of the macroscopic theory of superconductivity, we have the wave function of superconducting electrons, or maybe the Cooper pairs, in the top superconductor and in the bottom superconductor. So the analysis demonstrates that the absolute values of the wave functions will be the same on both sides of this dielectric barrier, but there may be a phase shift between them. So the variable phi, for which Josephson derived the Sine-Gordon equation, in this case, phi is actually the jump of the wave function, or the jump of the phase between the wave functions of the superconducting electrons, the jump across the dielectric barrier. So if x is the coordinate along this barrier, and this size is small enough, so this coordinate does not appear eventually in the equation, the final equation will take this form. In particular, this function sine is a manifestation of some fundamental properties of superconductivity. As a matter of fact, if, as I said, phi is the jump of the phase function, and the description of the system is superconducting electrons, it's not surprising that in many cases we may end up with a function which is sine or cosine of the phase difference. Okay, so as concerns the mathematical developments, exactly the same equation as Sine-Gordon in terms of mathematics has been known for a very long time, since the 19th century. And in mathematics, it appeared in a completely different context. It appeared in differential geometry. So people studied mathematically the shapes of some two-dimensional surfaces in the three-dimensional space, and there was a particular class of surfaces which were described as eventually exactly by this equation, by what is nowadays is called the Sine-Gordon equation. Actually, in this context, back in the 19th century, this equation was derived and studied by the Swedish mathematician Backlund. And in his work, Backlund made a really remarkable discovery. Actually, it was the first case when, in modern terms, in modern language, the exact equation was discovered. As I said, in the modern theory, the integrable equations, such as nonlinear Schrödinger, can be solved by means of the inverse scattering transform. The same is true for the Sine-Gordon equation. However, it's not the single method which makes it possible to produce non-trivial exact solutions. So what Backlund discovered a particular form of the particular method is a full method of the inverse scattering transform, but it represents its essential part, and this essential part makes it possible to explicitly demonstrate a large number of non-trivial solutions. So this mathematical method discovered by Backlund, as we see, as a matter of fact, 150 years, almost 150 years ago, it is a transformation from one solution to another solution, from a simple solution to a more non-trivial solution. This is called the Backlund transformation. So, first of all, one can, obviously this equation has, of course, a trivial solution, pi equal to 0. Then one can apply the Backlund transformation to the zero solution, to the trivial solution, and the result will not be trivial. It will be an exact solution, which is written here. So this is a stationary solution, stationary in the sense that it keeps a stationary form. It has a free parameter c. It may move. If c is equal to 0, it's quiescent. It's not moving. But we can also have a family of such solutions with any value of the velocity c from plus to minus 1. Actually, why the velocity is limited by 1? Formally speaking, this is obviously the relativistically invariant equation. And in terms of the formal similarity to the relativistic invariant equations, in this notation, the speed of light is 1. So this is a maximum speed which may be admitted by solutions of this equation. Therefore, we have this structure that c, the absolute value of c cannot be larger than 1. Now, this solution, as I said, it can be generated by the Backlund transformation, but one can very easily produce a solution if one does not know anything about Backlund. One can simply take this Sine-Gordon equation, as I mentioned, similar to how one can obtain the fundamental soliton of the nonlinear Schrödinger equation. It would be a result of a very simple exercise. The same is true here. One can just try to look for some solutions of the Sine-Gordon equation, which by definition, instead of being separately function of x and t, are only functions of this traveling coordinate, x minus ct. So one assumes that the solution should be a function of x minus ct, substitute these answers in the equation, and then it will, of course, be reduced to the ordinary differential equation. And then after very simple manipulations, one can produce an elementary solution of this ordinary differential equation, and it will be exactly what is written here. So usually this solution is called a kink. So the property of the kink, actually, there is some picture. Actually, this is already a set of two kinks, but we can, for the time being, just look at this part. So the kink is a solution which, when x goes to plus and minus infinity, it asymptotically has two different constant values. For example, 0 at minus infinity and 2 pi at plus infinity. For this reason that it interpolates between two different values of phase with a difference of 2 pi, this phase difference between plus and minus infinity divided by 2 pi, it is defined as a topological charge of the kink. So kink is the simplest example of what is just in one dimension, what may be called the topological soliton. I already mentioned that vortex solitons as solutions of the nonlinear Schrödinger equation in 2 dimensions, or in 3 dimensions also, they may be considered as topological solitons, and the vorticity is a topological charge. In that case, the topological charge may take any integer value, plus minus 1, plus minus 2, up to infinity. Here, in the case of the kink, the topological charge may take only 2 values, plus 1 or minus 1, because the solution only exists when it connects the values 0 and 2 pi or 0 and minus 2 pi. So in the expression for the solution, the topological charge is sigma. Sigma takes only 2 values, plus or minus 1. And that it corresponds so to the topological charge plus 1 or minus 1. And accordingly, such two solutions are usually called a kink or anti-kink. Okay, by the way, it seems that one can ask, so to say, a naive question: if this is a solution which interpolates between 0 and non-zero value to pi, why is it called a soliton? Because soliton is a localized solution, and so one should expect that the soliton should have asymptotically 0 value, 0 form, both at plus and minus infinity. In reality, this kink can be called a soliton. The point is that phi itself is a formal variable. What is observable in the experiment, for example, in the Josephson junction, phi itself is not observable. What are observable are characteristics, for example, such as the magnetic field of the configuration in this Josephson junction, and the magnetic field, as it's a part of this derivation of Josephson, is the magnetic field. It will be just the first derivative of phi with respect to x. It will be proportional to the local value of the magnetic field. So if one will look at such physically relevant characteristics like the magnetic field, everything will be well localized, because although phi has an asymptotically non-zero constant value at infinity, of course this derivative will vanish, and therefore we can still interpret it as a soliton. Also, its energy is finite; it does not diverge. Therefore, it's maybe interpreted as a soliton. Okay, so and then an essential fact is that this family of kinks is a completely stable family. So for all values of the velocity from plus to minus 1, it is a stable solution. Actually, in terms of in the application to Josephson junctions, kinks are always called differently. They have the name fluxon. The point is that one can call, because I mentioned that phi, the derivative of phi with respect to x determines the local value of the magnetic field, and integrating this field, one can calculate the total magnetic flux which is carried by the kink. And so the conclusion will be that the kink carries a quantum of the magnetic flux. So the kink carries a quantum of the magnetic flux, and the anti-kink carries also a quantum, but with opposite sign. For this reason, because the kink in Josephson junctions carries the unit or quantum of the magnetic flux, it's very often is called a fluxon. So accordingly, the anti-kink may be called anti-flux. Okay, then, so this solution by itself is an elementary one, which can be immediately found as a result of the simple exercise, even if we don't know anything about the Backlund transform and the fact that this is an equation which is also integrable by means of the inverse scattering transform. Now, what is very non-trivial is the fact that the Backlund transform, or the full method of the inverse scattering transform, it makes it makes it possible to create very non-trivial solutions which cannot be found in such an elementary by means of such as a result of such an elementary exercise. In particular, because the kinks can move with velocity plus or minus 1 naturally, similar to what we discussed for the nonlinear Schrödinger equation, one can ask the question, what will be the result of the collision between them? And the result is shown here. So this is a collision between a kink and anti-kink. So this is the initial configuration at t equal to 0. This is a kink, and then on top of it we build the second kink. So the first kink interpolates between 0 and 2 pi. Of course, this solution is invariant with respect to adding 2 pi times any integer n. So we can take the kink solution and simply add a constant term 2 pi to it. Obviously, it will remain a correct solution. So we can simply add 2 pi, and then this is how we can construct 2 kinks. The second kink is obtained as the original one plus the constant phase shift of 2 pi. Now we can give them opposite velocities. So this guy will be moving in this direction, and this guy is moving in the opposite direction. Therefore, they are going to collide. So they collide here, and as careful consideration demonstrates, in this case, they will not really pass through each other. They will always keep some distance. So they will attain some minimum distance, and then they will bounce back. This is something similar to what I mentioned today. Namely, I mentioned the collision between solitons of the nonlinear Schrödinger equation with opposite signs, in other words, with a shaped phase difference of pi between them. Okay, and here this is a similar situation. A kink and kink with the two equal topological charges, they repel each other. Therefore, when they collide, they don't really pass through each other. They attain some minimum separation, then they bounce back, and the collision eventually looks completely elastic, similar to what we have in the case of the nonlinear Schrodinger equation or in the case of any integrable equation. Namely, after the collision, we have exactly the same pair of two kinks with exactly the same velocities. So the original kink, it moved here, then it bounces back, and now it moves in the opposite direction. Another kink was moving to the left, it bounces back, and then starts to move to the right. And there is an exactly analytical solution for this collision, and it demonstrates exactly these properties. That the kink and kink, they collide elastically, bounce back, and keep exactly the same shapes and the same velocities which they had before the collision. Now this is another case, the collision between kink and anti-kink. Now this is, we can look at the initial configuration, this is the kink, and this is the anti-kink. So the kink connects levels of the phase 0 and 2 pi, and this one has this one provides the connection in the opposite direction between 2 pi and 0. They can be again imparted the velocities. So this one is moving to the right and this one is moving to the left. So they're going to collide. They really collide here. In this case, the consideration of the exact solution, which is available here, demonstrates that kink and anti-kink, they attract each other. They do not repel each other, but they attract each other. Therefore, they really pass through each other. And as a result of this passage, after the collision, we again have a kink and anti-kink pair, but now, strictly speaking, with the shift of the phase. For example, this kink, it originally interpolated between phases 0 and 2 pi. Now, after the collision, it will now interpolate between, it will be, as a whole, it will be shifted by minus 2 pi, because now it will interpolate between minus 2 pi and 0. So this is the result, result of passage of this kink and anti-kink through each other. So the overall phase shift by 2 pi. The collision is again completely elastic. They, except for this overall phase shift, they keep exactly the same shape, and they keep exactly the same two velocities with which they collide. Okay, then, because kink and anti-kink attract each other, there is a possibility to construct their bound state. So we already discussed the possibility of having the bound state in the integrable equation, namely the nonlinear Schrodinger equation. It was not a single bound state. It was a whole series of different bound states in the form of breezers of different orders, 2, 3, and so on. As I mentioned, each time it may be considered as a bound state of 2 or several fundamental solitons with different amplitudes, unequal amplitudes. Let me remind that, for example, for the second order breezer, it could be interpreted as a bound state of 2 solitons with the ratio of their amplitudes 1 to 3. Okay. In the case of the Sine-Gordon equation, we can construct an exact solution which represents the bound state of the kink and anti-kink. And in that case, on the contrary, which we discussed in the case of the nonlinear Schrodinger equation, it has a well-defined binding energy. So this is a true bound state, which is really supported by the binding energy. Therefore, it's a completely stable bound state. And it's all, by the way, it's also called traditionally by the same word breezer, for the reason that it's actually, it performs periodic oscillations. Actually, there is a picture to illustrate this. The picture is here. So this, now the bound state of kink and anti-kink is completely localized because it has zero phase, because it's a bound state of 2 kinks with topological charges +1 and -1. The total topological charge is 0. For this reason, it interpolates between 0 values of the phase of plus and minus infinity, and as concerns evolution in time, it performs periodic oscillations. So for this reason, it's also called the breezer. It's known in a relatively simple analytical form, as is written here. So the parameter mu is an arbitrary parameter, which means that we have a whole family of such breezers. So mu also determines the binding energy of this bound state. And so mu takes values between 0, it will be simply trivial solution, and the limit value is pi over 2. So it's exactly in the case of mu, which is going to be equal to pi over 2, the solution will take, after some consideration, the solution may be written in this exact form. So now, as a matter of fact, it's not a breather in this limit when mu becomes equal to pi over 2. The binding energy vanishes, becomes equal to 0. It's not a bound state, as a matter of fact. It's the limit case. It's actually the border between two different types of solutions, between the bound states and between kink and antikink collisions. It actually represents, as a matter of fact, the collision between the kink and antikink, but in the case when at infinity, when they're very far from each other, the velocity of each of them is 0. Then, of course, one can ask, if the velocity is 0, why do they collide? The point is that if we take an input in which we put kink and antikink at a very large distance with 0 velocity, still there is a very small interaction force between them. And as I mentioned it, when we are talking about the interaction of kink and antikink, the interaction force is always attractive. The same can be considered for a kink and kink. In that case, the interaction force would be repulsive. So under the action of the attractive force, these two fast separated solitons will start to very slowly will start to move towards each other, because even the zero initial velocities are 0, but they will be very weakly attracted to each other by this force, so they start to move. Eventually, this interaction force will accelerate them and they will collide. So all these situations, the limit solution both for the bound state and for the collision, which corresponds to the collision with a 0 relative velocity, it's represented by this specific exact analytical solution. The solution seems quite simple, but it is non-trivial, in particular before the discovery of the exact methods such as Backlund transform to generate such a solution. It was not known as a result of some elementary exercise. Okay, now let us proceed to another. Yes, as per the physical applications of the Sine-Gordon equation, I said that probably the most important one is the fundamental model of Josephson junctions, but it has also many other physical realizations. For example, it is a dynamical equation for some ferromagnets. So in that case, phi will be the local orientation of the magnetization vector, and under some special conditions, the dynamical equation for the propagation of magnetization waves can be derived. Under special conditions, it will take asymptotically the form of the Sine-Gordon equation. Then it has some applications in optics too. In optics, it may describe the effect which is known as self-induced transparency in some atomic gases, atomic systems, and it has many other applications as well. And so in that case, it may be we can say the same what was said about the nonlinear Schrödinger equation, or actually two nonlinear Schrödinger equations with opposite signs. We could say that these were ubiquitous equations which appear everywhere. More or less the same can be said about the Sine-Gordon equation. Of course, it appears in another class of problems in comparison to the nonlinear Schrödinger equation, but also in very many problems. Now, still another ubiquitous equation which has many important physical realizations and is very important also as a mathematical model. This is the equation which is written here. This is what I already very briefly mentioned today. It's called Korteweg de Vries or KdV equation. So this is the equation for the real unknown function u. It's a one-dimensional equation once again, because u is a function of t and x. Now this is the evolution term, du over t. This equation with a third derivative represents the effect of the dispersion. It's more or less similar to the dispersion in optics, but mathematically. So the fact that different plane waves have different group velocities depending on their wavelengths. Of course, here is described by another pair of terms, du over dt in the third derivative, but it's roughly speaking a similar dispersion effect in comparison to optics. And then this is a nonlinear term. It seems to be quite simple, but it's obviously nonlinear. It's a product of u and du over dx. The coefficient 6 is not necessary. It's written more or less by tradition, actually. Instead of 6, by rescaling, one can write, for example, 1. Exactly for this equation, the method of the inverse scattering transform and the concept of integrability were actually discovered. As I mentioned, the integrability of the Sine-Gordon equation was known in the form of the Backlund transform still from the 19th century, but at that time, people considered it as some exceptional case, and they did not think that it could represent some concept of integrability which may apply also to other equations. So the concept of integrability was discovered in 1967 in the classical paper by Gardner, Prosper, Mura, and the history which led to this discovery is the following one. The equation is called by Korteweg and de Vries because they published a paper back in 1895, at the very end of the 19th century, in which they derived exactly this equation from the full system, from the full Euler equations for the flow of ideal fluid. So they started from the full Euler's equations, and they wanted to very strongly simplify it in order to derive an effective equation for the propagation of waves, small amplitude waves, on the surface of a thin layer of ideal fluid. Ideal, this means that they completely neglected viscosity. They neglected many other things because they assumed that eventually this should be the situation only with two independent variables, t and x. So they consider the situation when the variable z, a vertical variable, could be eliminated because they derive the equation for the thin layer of water, roughly speaking, of the ideal fluid. And y, so in principle, if this is the equation for the surface waves, the surface has two coordinates, x and y. So by definition, they wanted to derive only the equation which for the surface waves, which depend only on one coordinate, x. And there is also quite a non-trivial equation when both coordinates, x and y, can appear for the surface waves. It's actually the equations that we will discuss a little bit later. It's called the Kadam's of Petriashvili equation, or KP. Actually, there are two different KP equations. We will discuss why. But Korteweg and de Vries, they consider the simplest reduction to the one-dimensional case. Also, in the process of the derivation, they assume that this is what is called irrotational flow. Irrotational means without any vorticity. And for this reason, actually, they could write it only in the one-dimensional case. Okay, so once again, what they did, they started from the full system of the Euler's equations, applied many simplifications, considered the propagation of the surface wave on a thin, I mean shallow layer of the ideal fluid, such as water. It's what we frequently called water waves also. And they ended up with this equation. So with this equation, x is the coordinate along the layer, and u has the meaning of the local. So if we consider this layer without any excitation, it will be a flat layer. And then if we consider some excitation, some generation of some waves, locally the wave will be seen if we have some local elevation of the surface. So we will have some shift of the local position of the surface from its unperturbed position. So we may have the the surface waves in the form of some hump. It means that locally the depth is a little bit larger, so the position of the surface will be shifted up, or it may be a local depression, and it means that locally the layer will be a little bit more shallow, and therefore the local position of the surface will be shifted a little bit down in the vertical direction. So U is the local elevation, the local shift of the position of the surface in the vertical or horizontal direction. Okay, so it should be also said that, as a matter of fact, exactly the same equation in the same context for the propagation of surface waves on a thin layer of water was derived almost 20 years earlier than by Korteweg and de Vries. It was derived by the famous French applied mathematician Boussinesq in 1977. But what happened was that Korteweg and de Vries, they understood the importance of this result. Therefore, they wrote and published a short paper, and in which they only presented in the brief forms the derivation of this equation and this equation itself. They also presented simple solutions of this equation, which could be found in the elementary form. And by the way, one of them was a soliton. We will talk about it. Actually, soliton is written here. So the simplest thing that one can do, if the equation is available, one can try to find a simple elementary solution, just similar to what I mentioned in the case of Sine-Gordon, just as some solution which is a function of the traveling coordinate x minus ct, substitute the ansatz, reduce this partial differential equation to the ordinary differential equation, and then it's quite easy to solve the ordinary differential equation and produce a family of solutions. They are written here. They depend on one free positive parameter c. C determines the amplitude of the solution, simultaneously determines the velocity. So this solution may exist only when it is moving, because if c becomes equal to 0, the amplitude also falls to 0. So the solution lives when only in motion, and then it is a family of such solutions. The analytical form is different from what we discussed in the case of the nonlinear Schrödinger equation. With nonlinear Schrödinger, it was 1 divided by hyperbolic cosine. Here, the formal difference is that this is 1 divided by the square of hyperbolic cosine. This difference is related to the different types of the nonlinearity. In the nonlinear Schrödinger equation, nonlinearity was cubic, and the cubic nonlinearity naturally generates in its solution the form 1 divided by hyperbolic cosine. Here, the nonlinearity is quadratic, and the quadratic nonlinearity in this elementary solution naturally generates the analytical form 1 divided by the square of hyperbolic cosine. So what Korteweg and de Vries did in their classical paper, they wrote a rather short paper. They briefly presented the derivation, the equation, and simple analytical solutions which could be found in this form. And since then, it's known by their names. Boussinesq, instead, he wrote a very, very long paper, in French, what at that time this long paper would be called by word memoir. He wrote this very, very long memoir about different solutions for different model equations, which can be somehow related to hydrodynamics of ideal fluids, to water waves, and all that. And somewhere in the middle of this very long paper, this KdV equation was hidden. Because it was hidden in the middle of this extremely long memoir, people were not aware of it. Moreover, actually, at that time, it may be when Korteweg and de Vries published their paper, it was already important in what language the paper would be published, because, as I mentioned, this memoir of Boussinesq was published in French, and maybe by the time not everyone would read French, but Korteweg and de Vries, also they published it relatively long ago, in 1895, they already published it in English. By themselves, they are Dutch. They were Dutch scientists from the Netherlands. Of course, they had no idea to publish it in the Dutch language. No one would read it, but they picked up a correct idea and published their paper in English. And so their result became very quickly, very widely known, and since then it's called the KD-Korteweg-de-Vries equation, with a footnote that, strictly speaking, for the first time it was derived by Boussinesq. Okay, then, as I said, there are elementary solutions, which were already found in the very first paper by Korteweg and de Vries. So these solutions are simple localized waves which can be traveling with different velocities. The velocity may have only one sign, C is positive, but the velocities may have different magnitudes, and therefore, of course, solitons may collide. So you can create a faster soliton behind the slower one, and so it would overtake the slow soliton, and they inevitably will have to collide. And therefore, at some people eventually got interested what will happen if the solitons will collide. And for the first time, where people didn't know anything about the integrability, it was studied by means of numerical simulation. So the first systematic simulation of collisions between KdV solitons was performed in a famous paper, which I mentioned already, by Korteweg and by Kraskell and Zabusky. It was published almost 60 years ago, namely in 1965. And what they did, at that moment they still didn't have any theory, but actually in 1965 still the scientific numerical simulations was something which was not very common. It was something which seemed relatively exotic, but already at that time, Zabusky, he was one of the first experts in scientific simulations. He already have at his disposal a sufficiently powerful computer, a very weak computer in comparison with any modern laptop, of course, but for that time it was a strong computer which was able to simulate solutions of this equation. He simulated the collision of two solitons with different velocities, and what he observed the exactly elastic collision. The faster soliton would hit the slower soliton, would pass through it, and if the simulation could be run for sufficiently long time, eventually they would observe exactly the same set of the solitons, slow and fast, with exactly the same parameters, exactly the same velocities, and also with what I mentioned already, the only effect of the collision was some overall shift. So after the collision, the faster soliton would be found at the position which was a little bit shifted ahead in comparison by constant distance in comparison to the position which it would feature without any collision. So this is how this property of the elastic collisions between solitons was discovered empirically in the simulations in 1965, and it was a very strong hint to the fact that there should be some mathematical structure which produces these absolutely elastic collisions. And then 2 years later, this discovery was made, and the classical paper was published by Gardner, Kraskell, Green, and Mure, and they found the possibility, they found the inverse scattering transform, which demonstrated the integrability of this equation. Of course, it's a very particular case. This method demonstrated the exact elementary solution, but as I said, Korteweg and de Vries themselves were able to find this solution without knowing anything about integrability. But for the first time in this classical paper, they had the exact analytical solution which demonstrated absolutely elastic collisions between solitons moving with different velocities. So this was an extremely important step in the development of the mathematical theory of partial differential equations, and also in applications of these equations to many physical problems. Okay, I guess I will have practically come to the end of this double.
Yes.
let me just say what will be the continuation. I mentioned today in a couple of words that, for example, if one wants to derive again the equation for the surface waves on shallow water, but taking into regard the possibility that this will be a two-dimensional equation because we have two coordinates x and y on the surface, one can derive the effective two-dimensional equations. So these are also very famous equations, which are called Kadants of Petriashvili or KP. There are actually two different such equations. Why two different equations? We will discuss it. And this will be the point from which we will start the next lecture in 2 weeks from now. And for today, thank you very much for your interest.
Okay, thank you very much, Boris. Thank you. Your next lecture, the next lecture is for Tuesday. Your next lecture for Tuesday, October 10. Mean that next Tuesday on October 3rd, only Alain will give the lecture, 3 hours of lectures. And before that, this Friday at 3 p.m., Alain will give a short communication, a talk at 3 p.m. Okay, thank you very much. Thank you all.
Okay, thank you. And as concerns myself, see you in 2 weeks.
Okay, thank you.
Thank you.
Bye-bye, everyone.